number one, just using tabular data, how to think about your problem. I think just from a real world case, some of the modeling from the first talk from around COVID data, then Atik and Saptashi's talk, which was, I think, excellent in trying to just explain some of the machine learning concepts, and then followed by Minje's talk, which is trying to say, here are some of the statistical errors. So it's really a cycle, right? It's not like you're one and done. So be very careful of your test set and how much you reuse it, because the more you keep going round and round, you can have a perfect result. But I hope right now you're starting to feel some of the tools that you have to improve your portfolio for approaching machine learning. So, the one thing I love about the participants today is everyone is not short of how to make ideas better and how we're making this better. One of the things is I put the slides on. My slides are already on the Slack channel. I know Awez is going to put it in where everyone can find, and he'll show you at the end where you can find all the slides. Professor Odom brought this idea of these cards. When we're helping people, it's hard to know where people are. We're not going to have a hands-on for my session, but every time we have a hands-on, we just want you to pick up this type of card and just put it at the back of your laptop if you're having a problem, right? So people can see where you are and come and help, okay? And then, outside there's 50 fun things to do in Atlanta, so make sure you pick this up. And I would also like to acknowledge Dr. Newsom, who's at the back there. I showed you she's one of the faculty of the HITI lab, and she finally was able to join us in person, but I know she was following what was happening. So I'm going to talk about the patient's imaging journey. And, this is a talk I actually have adopted from one of my mentors. He's called Mark Coley. He's at UCSF, looking at the life cycle of an imaging exam. This is even after I'd done my work for informatics, I still found this very, very challenging. And I hope that this is going to be a basis for quite a lot of work that is coming downstream. So I'm going to talk about standards relevant to imaging workflows, and then discuss the imaging workflow, and then summarize why the imaging workflow is important in the context of AI deployment and training. And so there's this thing called HL7. How many people have heard of HL7? Ooh, okay. So HL7 is a standard. If you assume we are all in the room and we decide to text each other, now we only understand, if you texted me in Yoruba, I wouldn't understand it, right? But we assume that the recipient of your SMS message is going to understand the language, and the only work T-Mobile or the national telecom provider does is to make sure that the routing goes to the right person, right? So in healthcare, it behaves the same way, but the way to send messages, so for example, from Mayo Clinics to Emory, has to be in a structure that both mobile devices are going to understand when they send and when they receive the message. So that standard is called HL7. There are many versions of HL7. This is version 2. It's the most commonly deployed. Unfortunately, it's very variable just based on the institution and how it's implemented. And there was an attempt. All of us know that XML and JSON at some point were the only data format that you could have. And so there was an attempt to move to HL7 3.0, but not many organizations adopted it, because imagine all the labs that you have to send and where you have to send them. If you have to go back and rewrite those, it's quite a lot of effort. And so it's very difficult to do. And so version 2 and 3 are not compatible. So if you find out, you have to know the type of data that I'm expecting to receive, right? And the type of data that is being sent. And so what we are seeing today, if you're, for example, my colleagues, a lot of colleagues from Kenya, if you were to implement something, you'd use something called FHIR, which is a standard that allows you to use a RESTful API. Things are represented in pretty much the same way, and it abstracts sort of the back end and the complexity of deployment of this standard. So this is an example of FHIR, and you can see sort of like different things, like what's an appointment for scheduling, or what's allergies or a device, and so this is anticipated to be the future. Yes, I am sharing screen. Oh, probably the AV person at the back there is not sharing their screen. So, so we all of us understand the success of the web, right? You send a request like to datathon.org and it sends you a response, right? What facilitates that exchange is this sort of standard, about like get and put, and we see the same sort of, these are some of the HTTP methods. You can get, put, post, delete something. It's a very common standard. And so the standard that is used for medical imaging is actually called DICOM, and I'll show you an example of that. And it behaves, you can have like REST for DICOM, it's called DICOM Web. And this is because if sometimes you were to show me my picture of a chest x-ray on my phone, right, you'd have to render it using a web format, right? And that's enabled using sort of this DICOM Web that allows you to query, retrieve, store, and update some of the things. So pretty much the simple thing, the things that allow us to communicate healthcare data is HL7, and for medical imaging is DICOM. So let me talk about the imaging workflow. So you have everything. I told you that you have like a mobile provider, that T-Mobile, Verizon, or anything else, that is here and acts as an interface. And you have all these other systems that are always controlled by the interface. And we're going to look at this. This is a picture I took of sometime this year earlier. This is in Kenya. It's Tsavo. Tsavo National Park is, there's a movie called The Man-Eaters of Tsavo. Very, very big elephant, African elephants. It's amazing to visit. So we're going to image an elephant because in another life I'd probably work in the Wildlife Service and enjoy being a radiologist for elephants. So we're going to image elephant Rex during this. So let's assume the elephant has right upper quadrant pain. Okay, so everything starts with an order, right? The doctor orders something to be done. You can see that this is an order requisition form that has elephant Rex, right upper quadrant ultrasound for right upper quadrant pain. It's signed by Dr. Bob and the date. Okay, so let's start off with an outpatient system. And this is done more from like how the North America regions would do something like this. I recognize and I'll highlight why it's a different way from outside the US. And so, Rex has right upper quadrant pain. He comes into the radiology department, and the first place he goes into is registration. And so in the registration, this is done in the electronic medical record system, where elephant Rex, we collect the demographics, that we have a medical records number or generate one, and we also collect insurance information. And then this EMR generates what's called an ADT HL7 message. And ADT just means admission, discharge, and transfer. It's just registering, a patient when you come to the hospital. And so the EMR, which is here, the electronic medical record system, sends a message through the interface engine to all systems that need to know that there's a new patient who's called Rex. Okay, here's an example of, wow, it's really chilly here. It is actually, so the EMR generates this message, and because it needs to have one source of truth for the medical record number for the patient. And so here's an example of a ADT message. It's not supposed to intimidate you. It's just showing you sort of like they have this character, and I'm going to, zoom in. You can see that this is the hospital header, and then the medical record number, and sort of who, sort of who's ordering. And so the ADT messages can be used to do admissions, can be used to do transfer of patients, can update patient information. Just what you need to identify a patient is really captured in an ADT message. So once the registration is successful, the patient Rex goes into the actual scanning area. And so when you go to radiology or the lab, what you find is this workforce that is called radiology information system or a lab management information system. And this is, the clerk will look up and say, okay, I know Rex, it looks like you're registered in the system, you've paid or your insurance has pre-authorized, right? And then so let's scan you. And so we pull up this order, and now what we get is what's called an ORM message. Don't worry about cramming this, and actually everyone has the slides. But when you get the ORM message, it's really coming to the workforce for the radiologist, which is called the Radiology Information System. And this system now generates a unique accession number, a procedure code, and a procedure description that is going to be important for any subsequent, for any of the subsequent like scanning of the patient. And so because now we are in the RIS system, we have this ORM message that goes to only the relevant systems for radiology. And so here's an example for an ORM message. I'll zoom in. You can see that it has this segment, for example, saying Rex has right upper quadrant pain, so it updates this type of information. So in imaging, we just have cameras. It's just like our cell phones in different types of cameras. So in this one, I'm showing you an ultrasound. And, the ultrasound interfaces with the PAC system. The PAC system is just a database for storing medical images. And the way these two interface is through something called a modality work list. And why that is important is because you need to be able to not enter the information in the system. So Lois, Baloa, Jasmine may not really have, and I'm only calling on them because they're Kenyan like me, they may not really have these fancy systems, right? The patient comes, they verify that they have paid, and then they just come in and, are you donating your sweater? Okay, thank you. It's a little chilly up here. So, they come in and interface with the modality work list. And the only reason for that is to make sure that you're not entering the medical records numbers again. That's important because all of us, we're going to be working with longitudinal data, right? We need to make sure the MRN is the MRN, right? That you're not identifying Judy with 5 different MRNs. And if you do, then you need to be able to harmonize that data and clean it up, right? And so, so if you look, now this is the interface that you'd see, for example, on an ultrasound, and then you search for elephant rex. So Baloa would be entering these things manually, but here, most of us will just pull up the details that you need, and then once you pull up, then you'll see, oh, okay, Rex is here to have a right upper quadrant ultrasound, and then so here's Rex, and here's your ultrasound scanner that you're going to scan the elephant, and you can see that this is the ultrasound itself. You acquire the images, so these are 3 images of the right side of this. This one is just showing a kidney, some blood supply, and the liver. And so now you need to move these images to the database, which is the PAC system. Now, I talked about DICOM, and I want to just go back to it because it's very, very important, and you'll see why. So DICOM is quite a confusing standard. It's an old standard. That's why you can buy any radiology machine, and it works, right? It's because of this DICOM standard. And it's because it's a network protocol. It's a file specification. It has so many things. For example, these are 22 things, right? You can see how you can exchange messages. You can see, for example, here's a snapshot of anything related to AI. If you're a developer and you're trying to build radiology imaging things, this is how you do it. So it's quite a detailed standard, and you can read about it. So we're taking a lot of pictures, and I encourage you to keep taking lots of pictures. So here's a picture that has been taken of an anatomy segment. If you were to say, show me the metadata of the picture, then you would find this type of information, right? The camera, in fact, right now they even track the GPS of where you took the picture, the type of, the resolution, the date, all these things are metadata of just a normal picture in our phones. It turns out that medical imaging has the same as specified in the DICOM metadata, right? So you can start to see the manufacturer, the hospital name. Lois will appreciate this because this is where she works. You can see sort of a lot of information is put in, some are missing, and is put in the DICOM metadata, and it's just the same. And then if you're very, very obsessed and very meticulous about how you organize your medical image, not your medical, your normal life pictures, you may have, for example, you organize them in a parent folder that represents the year, then the month, and then you have subsets of the pictures. And in medical imaging, we have the same sort of organization. So you have a patient at the top, and then a patient can have multiple studies, and every study, this is super important because you're not going to be able to work with medical imaging data if you don't understand this concept, okay? So I'm gonna slow down and just explain this a little more. You start off with a patient, then patients can have multiple studies, a CT scan, chest x-ray, ultrasound, and every study has series. For example, an axial image, a sagittal image, a coronal image, and every series has an instance. Okay? This will be repeated again, but this is the fundament, because you have to decide when you're splitting your data, are you going to do it at the study level or the patient level? You know, are you going, you know, so there's so many nuances that you have to decide. Are you going to do a 3D versus 2D study? And that's the rest of the sort of like the workshop. So you have images, you need to send them back to the database that stores images. So you push the images, and when you push the images to the PAC system, then you have an update of the ORM message that says the study has been completed, there was contrast that was used, the performing technologies, and there's some technology comments. So all this can be data that can be mined, and it's usually encoded in the, you know, sort of the DICOM metadata. And once that does, the RIS sends these ORM messages to just the radiology-specific systems through the interface engine. So here's an example. The radiologist usually works through a viewer, and here's a very popular open source viewer called the OHIF, and you can see that I'm looking through a coronal image, which just means it's just the way you're looking at me or how I'm looking at you, just straight through your body. These are actual images. You can see there some are different windows, right? So these are different series of the study, right? So you have to remember that hierarchy. And you know, all of us, all we do is we have this viewer, and we're just picking studies that are completed and interpreting them. You know, that, so you have to differentiate a little bit between a viewer and a PAC system, although some places where there are not enough things in the you don't have enough resources, use the PAC system as your viewer, but that's not the ideal way. So then, if you're in a resource-rich area, you'll generate a report text that can be below types here in Word, but for us, mostly in the US, we dictate this using a system, so a voice recognition system, and once you finalize it, you have an exam status, a dictating radiologist, and accession number, and all this now become an ORU message, which is just a result. So the RIS, again, you know, receives the ORU message from the voice recognition system, and once it receives it, it sends the ORU message to all these other systems to tell the EMR, hey, I have a final report. Now the doctor can see the result, or hey, this is a critical result. We have a database, or the PAC system. And so the ORU message, you can see a more detailed one here, that there was upper quadrant ultrasound performed in 2011 for pain, and the liver is normal, blah, blah. This is the result, and you can see who transcribed it and what was the final impression, which is the gallstone without acute cholecystitis. And so Rex leaves, you know, the department with a report, and the doctor is aware of the result. So let's talk about that imaging workflow in the context of AI. So you always have the you always have the interface engine. So you have to ask yourself, where do you identify patients? This has been a lot of painful lessons between me and Harry over the years. I know Chad is smiling because they have also generated a lot of text messages and emails to him. You can identify your patients from the electronic medical record, right? This, I think most of us have moved to having this as the sort of the truth. And most of these cohorts, you can either say, I want all patients with chest x-ray, or you can say, I want all patients with a diagnosis. Now, remember what during Saptashi's talk when we talked about the challenges of ICD codes, and if you use those to tell you this is the diagnosis, right? So you have to identify, where can you identify your patients? You can identify them through your picture like a park system. Remember, the parks are usually many layers of parks. There's like you can imagine it as a deeper archive park. So for images that are not used 3 months, they're pushed to a more deeper system to save space. In Tanzania, where Baloa works, they delete the images, right? So those may not be available. And you can also have some data stored on the modality, but the modality has a small hard drive and it's going to get full and you have to delete it, right? So for us, because we work on bias, we have to think about completeness, and sometimes we just have to look at all the places and see which cohort of patients are missing. That may be absent when you come downstream. And then, you also have to think about the feasibility of the longitudinal data set curation. So one of the implications for this is not just cohort identification, but the data set labels and where the reports stored. So in our EMR, the reports we figured out how to get them out, but they usually can be very broken down. They lose their structure. In the voice recognition system, we can get our reports, and in the RIS system, sometimes you can get, and it's not very easy to query the reports in a PAC system. Now, I want to talk a little bit about an initiative that you should be aware of. This is the common data element. Even if you're not dictating with these common data elements, they're important to try and tell you what labels should I be thinking about for my radiology report. And so like Emory, for the 5 years I've been here, most of us use some form of semi-structured report when you sort of look at your report. So if you were to analyze or build your NLP model to label test X-rays, from 5 years ago versus now, your model performance may not work well just because of the structure of the report itself. But the common data element is all about the language of the radiologist. And so here's an example. For example, they say if you have to describe arterial calcification, you should either say that it's either absent, present, indeterminate, or unknown, right? So those 4 things are the possible labels you could attribute your data set. And so you do still have to think, are the reports structured and where they are? So by the time they get into the EMR in our own institution, they're not very useful. The structure is lost and you still have to build your NLP system for doing this. So our own data curation pipeline, you can talk to Harry and Awez and Beatrice about this if you're more curious. We moved to Sectra, which is a PAC system. This is our storage system from GE, but we have data in both systems. Then we extract our cohort, and then we have a hybrid setup that one runs on the cloud and others doesn't. And then we de-identify. So the reason I'm showing you this is that you have to identify the DICOM metadata. You have to de-identify the images themselves, right? Because they could have some PHI, protected health information in the image itself. And you have to de-identify the tabular data you got from the EMR originally to build your cohort. And then you have to keep all those things in sync, and the 4th step we do is manually inspect the images to also not only see that if you're missing some PHI information, but also to see that the PHI de-identification is not destroying the radiology images. So this is quite an intense process to get better. I think we have over 1,000 tags in DICOM that we know how to treat, but we get more information by testing even other commercial softwares. And so when it comes to AI deployment, is very dependent on the DICOM. And you have to decide, are you going to deploy something that works on the images or the text, right? Because then you can see that the point of deployment is different. You have to decide whether you're going to integrate with something that integrates with the work list that the radiologist sees. Are you going to run a silent trial so you're not going to be demonstrating results, right? Because then you may have to have a delay or that there's no way to really curate HL7 for something like that. It's going to send the result. You just have to hide it from the radiologist or send it somewhere else. A lot of people send, they'll have a different architecture that just is listening and sending the data there. Some of the new work is deploying the AI on the modality so that when they get the image, it makes a decision. For example, if it's an endotracheal tube or support device, if it's malpositioned, it just puts an alert when the X-ray is still in the patient's room so that it's corrected and another X-ray is acquired. And then you have to think, where do you want to send the images to the PACS, and will the radiologist see your result first or afterwards? And so if you're going to be a company that develops, or you're thinking downstream where your AI has to be, you have to understand the imaging workflow. So coming up to wrap up, we in deep learning deployment, DICOM is super, super important in terms of processing. You can see these are different images. I'm not going to take Theo's talk. I'm just trying to put in a plugin. It's going to be the last talk of the day, and it's going to show us why this processing is important. Now, this is very mature for radiology images, but all other images are moving to this concept of enterprise imaging. So, for example, Embed, in a few months, we'll have the pathology slides, right? So it's not just going that when you build your AI model and say this is cancer, we can really see what the pathology slides is going to look like. And so it's this concept of enterprise imaging that transforms cardiology, orthopedics, anesthesia, pretty much any image that is captured to wrap around the DICOM format so that they can be displayed on these enterprise viewers, and they maintain that streamlined accession metadata that has allowed radiology to really be successful in terms of developing AI. So I hope that at least you have a sense, and it's going to give you some context of understanding what the imaging workflow is, what is this DICOM, and especially in the context of AI along the whole life cycle. And my assignment to you is to think about, especially if you're here as someone who's going to get your own data set, sketch your data curation pipeline, and whether you're developing or deploying AI, and what that's going to take at every level. And if you're missing something from this cycle, it's fine. You just have to say, I'm going to identify patients from this, and then I'm going to do it this way, because that's going to help you understand how to build your cohorts. And yeah, so this is just an introductory lecture to DICOM. Was it understood? Okay. Cool. Okay. Yes, Zeph? Uh-huh. Oh, sorry. Mm-hmm. Mm-hmm.
The face. Yeah. That is a unsolved problem in medical imaging. So the question is, um, if you take a CT or MRI of the brain or of the face, and if the slices are thin enough, let's say less than 2 to 3 millimeters, you can do a 3D reconstruction of that image, a surface reconstruction, and see the patient's face, right? And there's an area of research here to deface these models, because deface these scans, because if you release them publicly and somebody does a 3D recon, um, you can potentially identify a patient similar to having a photograph. So um, it is. So I actually participate in a few initiatives around this. The largest one being the Bridge to AI program. Emory's a member. We're part of the Chorus consortium. We are evaluating a few different solutions, but there is no perfect solution. So some of them, what they do is they try to identify landmarks like the face, the bridge of the eyebrows, the nose, the lips, and chop them off. So that's one option. Another option is to add pixels, right? So turn the head into a rectangular block, right, by adding pixels. But that's tough because you imagine if you normally in front of the face on a CT scan you have air, right? So you have to fill those pixels with something else that closely approximates whatever the tissue was underneath. Otherwise, you could just subtract out those fake pixels, right? The other solution is to most models that use brain MRs or head CTs are interested in the brain and not in the face. There's not a lot of AI models in the face. So the third option is actually just segment out the brain and the skull and remove everything else, since that's what you're going to train the model on. And there's challenges with each of those. as many of you probably know, deep learning models are very, very sensitive to variations in data, right? So if you train a model on a brain MR for, let's say, brain tumors, and all of those MRs have been defaced using a certain piece of software, if you then try to run inference on a different set of data that's not been defaced or not been defaced in the same way, it's very possible that the model will fail, not because any of the brain tissue is different, but because the statistical distribution of the data is different. So it is a big problem. Data brokers are already selling data with faces in there, and the go-to standard right now is to make any purchaser or user of the data sign an agreement that they will not attempt to reconstruct or re-identify, and that's sort of the only questionably legal method to do it. Yes.
So, yeah.
They get compressed on the scanner when they're reconstructing.
Yeah, but not too much. We really read very high pixelated images, right? So this is a problem with training machine learning when your breast cancer is like a dot, right? And you've, and this has come out, I think, in Monique's and Duhau's talk, the whole image classifier versus this like downsizing that we do. But most of the time it's because of streaming, right? So when you're sending the image, and sometimes they'll like compress during the streaming, and then but we read on very high resolution monitors, and that's very important for radiologist performance.
And to answer your question a little bit more specifically, so any compression that's done on the image is typically done at the modality. So CT generates a sinogram, which is its raw data, reconstructs an image. That image is saved into a DICOM file at the scanner in whatever compression format. Of the ones I've seen, and I'm not super familiar with this, so somebody chime in if you are. I've seen like lossless JPEG, for example, as a compression format. Once it arrives to PACS, the PACS systems is essentially an archive, right? So it doesn't touch the data. When we retrieve it, we also don't touch it. Now, whatever you do downstream of that to train your model, right? You do your PNG conversion and whatever transformations you apply, that's different. But it is safe to say that when you retrieve images from the PACS system, you are retrieving them in the format that they came off from the scanner natively. Yeah, so great question. So there's the question was how do you
Link.
track multiple scans from the same patient, right? So there's a concept here, anonymization versus de-identification. Okay, so anonymization is when you replace all patient values with fully anonymized or random or hashed values and you throw away the key. It's irreversible, right? So if you take a cohort of data like chest x-rays for 100 patients that have 5 chest x-rays each and you anonymize it, you will, depending on the method you use, if you're not storing an intermediate key, every patient, you will not know which x-ray belongs to which patient. The systems that we use typically in our lab, and if you look at medical data sets, is they actually use we use them interchangeably, but technically it's a de-identification system. So you are at least at some intermediate stage tracking an original ID being mapped to a new de-identified ID so that 5 chest x-rays from the same patient can receive the same new de-identified number, right? And also the date shifting. So we didn't really touch on this, but when we de-identify, we want to shift the dates. Now, if you shift every exam in your data set by a random amount, you will, if you only have one exam per patient, that's fine. So if you have 100 patients, each one has one exam, you can shift every exam by a random amount. And at that point, you probably don't even care about the date, right? Because what's the point in the date? Dates become important when you have 5 scans from the same patient. So what we do and what most groups do is when you de-identify, you select a random date shift for a patient, and then you de-identify and shift all the exams, all the clinical data, all the notes, all the ICD, CPT codes, everything for that patient, you shift it by the same amount. So Sally Smith is going to get patient ID 1234. Her date shift will be minus 37 days, and that is stored, right? So next time her scan comes up, or a clinical value or anything, it's shifted by the same amount. And then John Doe comes, his random assignment will be plus 24 days. He'll get a new patient ID. So you maintain the temporality between all of the x-rays, all of the clinical data, all of the notes, all of the records. If you don't do that, you will more or less destroy your data set, right? So you really have to be careful.
You should keep forever, really, in machine learning, but
Yeah.
the legal one is 7 years.
7 years legally. Typically, our archives go back 12 to 15 years.
One last.
Saptarshi,
Yeah.
Yeah, so my question is a follow-up to what the question was during modeling session. So each of these modalities might change over time, and that DICOM information might get lost when you're trying to build a model.
Yeah.
How important do you think can you reflect on capturing that modality information within that image or within the DICOM? How do you balance it? And because it has effect on the model.
Yeah, so I think one thing that we've done a lot of this has been, we keep our data now in DICOM format. It's very efficient to transform it to, your final image, but there's so much information in the DICOM metadata and also in the image itself, as you'll see from the pre-processing, that if you had just JPEGs, you'd completely lose. And so I think the best standard today, most data sets are not released this way, I would say for imaging should be in DICOM format. You should just make the attempt to de-identify the images.
And I'll add one point to that, which is I've been working with the DICOM working group for OMOP or like peripherally with them and trying to decide, for example, for this bridge to AI, which DICOM elements are going to make it into the OMOP tables. It is you can develop a reasonable list of 20 or 25 tags that are, so DICOM tags, it's a public dictionary of DICOM tags. There's nearly 1,000, of which maybe 700 are in use regularly. And that's just the public tags. And then scanners have private tags. Of those 700 tags, probably 20 to 25 are usable or useful for machine learning development. So our idea is to take those 20, 25 tags, store them in OMOP tables. The remainder of the tags largely sit untouched inside of the DICOM files if you need to access them. But what you don't want to, like what we try to do is we try to pull out DICOM tags and store them in some table so that you can look up information about the DICOM files without having to crack open each file. And we'll talk about that a little bit because that's a computationally expensive process every time. So a single MRI might have 1,000 DICOM files, right? And so your whole data set, our breast imaging data set, has 3.5 million DICOMs. And that's pretty small compared to other MRI or 3D data sets. So if every time you need to get metadata, you have to crack open 3.5 million files, you'll be in a world of pain, right? So we try to store that data outside so we can, like in a Parquet file, for example, so that we can access it more easily.
Okay, let's go for a break, and we will be back at 3:10 for Dr. Van Assen, who's back there to tell us what should you be thinking about chest x-rays and some of the pitfalls. So thanks.